Hi everyone. Welcome to Linear Momentum. This is I guess this is episode 7. So in the beginning we've covered so far is kinematic equations, which were very heavy with math, and they were light on the they were light on the physics and more heavier with math, right? And then we did 1D kinematic equations, 2D kinematic equations, which was the heaviest video I uploaded, and then we did 3D relative velocity, 4D space-time. There was a typo on those episodes. So other than that, after that we covered forces, and then we did energy. We talked about wherever there was but we're going to really start off from forces with this, with linear momentum. So to understand a force, right? Anytime that there's a flux, remember we talked about, in forces I talked about equal pressures acting on the system. We considered force to be like a flux. Whenever a force is acting on an object in equal and opposite reactions, we could all, if the force is in equilibrium, then we say the sum of the force is equal to 0. If the force is moving, then it's mass times acceleration. But the velocity is constant, so we no longer care about velocity as we did in kinematic equations. And then if the force has an equal and opposite reaction, it acts like an equilibrium force in a way. That's what's interesting about Newton's laws. Newton's third law is kind of the same thing as Newton's first law, but Newton's second law is the opposite. So an equal and opposite reaction can also, it works almost the same as forces that's in an equilibrium position. So I wanted you to think about that. Other than that, I don't know if we should do orthogonality or not. The way I want to do this video is I like to just do the math first before we get started with the physics, since math is the foundation to physics. Physics is the application of math. So what I will do is I will try to show you the math that's held responsible. Now we're talking about linear momentum. Linear momentum is what we're understanding now. Now, when I talked about energy, when I did forces, I should start from there. I showed you which diagrams are important, which about the influx, about flux, flow in, flow out, junction in, junction out, the scattering matrix. I showed you all that stuff. You just got to watch those videos. Other than that, that is what you're going to be doing if you want to follow my method. So you go from there, and then we talked about where we talked about forces, how there were conservative and non-conservative forces, and then we talked about when work is acting. When I do work onto a force, I end up getting what's called energy. Now, if you think about it, I didn't get to say this in the last video, and I guess I had the right idea not to, but you can think of energy as an impulse, right? We said force was a vector, and then I showed you how energy, time, and mass are scalars. So we learned vectors so far. We learned that position is a vector, velocity is a vector, acceleration is a vector, time is a scalar, right? And mass is a scalar, and energy is also a scalar. Now, momentum is a vector. It's not a scalar. So one way you can think about linear momentum is it's a reenactment of energy. It's like energy being a reenactment. It's almost like you have the Revolutionary War, and then you do like the Cold Spring Village reenactment, or you do like a Civil War and you're reenacting the war that took place. You can think of linear momentum as a reenactment, like a historical reenactment. Other than that, it's a really healthy way to think of it like that. See, linear momentum is kind of mankind's perspective, I should say, on energy. Energy is a very natural phenomena. Right? It exists in nature, and it's how we define God and the universe. In nature. Now, when we try to measure something, we're going to consider it to be momentum in our own perspective. Just think about that. This is deep. And another way to understand it is a wave is a natural phenomenon, which you don't need to worry about waves in this because we're only caring about linear. Waves don't exist in this season. A matrix is a man-made tool to measure the universe. See, I like to show you nature, but I like to show you the tools we use to try to measure nature. Okay. Enough of that. I just like to explain the philosophy of it before we get started. I was actually interested of who came up with collisions. Like, who came up with the idea of linear momentum? And for some odd reason, this is not mentioned in physics textbooks, just like the issue with Galileo made these Galilean equations and Newton invented the last kinematic equation. Because the first video, when we did 1D kinematic equations, remember, well, if you watch the first one, I called the first 3 Galilean equations, the last one Newton's equation. Now, with momentum, I wanted to know who developed momentum. And for some odd reason, which it really drives me, like, mad, is that textbooks don't even put it in there, like, who the person that came up with momentum. And I will tell you on this video. It is a German rival of Isaac Newton, Gottfried Leibniz, came up with linear momentum. He's not mentioned for some reason. He's a mathematician, a polymathematician, but he's not mentioned in any physics books. It's almost like, it seems to me like his name was just taken out of the books for some reason in academia. But if you want to know who came up with collisions and linear momentum, it's Leibniz. Now, there were other people as well as him. There was Sekikawa in Japan, but they really didn't practice physics. They just stayed with the mathematics. They had a very interesting way of understanding math. So the way they did integration was a method of, they actually did antiderivatives without doing the calculus. They used a series. So they did like a numerical expansion, which is known as perturbation theory, and you're trying to approximate the numbers as close as you can. It's almost like trying to match a decimal to a fraction. And you can think of it as an irrational number. So they ran with this concept. They ran with this thinking of series and expansions, and they managed to come up with integration that way. And I'll save all that when we do multiple integration. There's a Japanese word for it, and I am not going to spill the beans on that yet because I want to keep that a surprise. It's going to be on the episode, by the way. Over the winter, I'm planning on doing integration by parts, but I'm going to also do partial integration, which is not the same thing. Partial integration is like double integrals, and we'll talk about this. There was a Japanese mathematician who came up with double integration, believe it or not. Triple integration was never really discovered in Japan, but they actually came up with double integrals. And triple integrals are the same thing, but like I said, integration by parts and partial integration, they're not the same thing. They sound the same, but they're not. I thought they were the same thing when you're in Calculus 2, but when you're in Calculus 3, you find out that they're not the same thing. I'll probably, in the future, do a video on partial derivatives. Other than that, if I ever show videos on that, I'd rather show you like antiderivatives, which are integrals, before we do derivatives. But other than that, we've learned derivatives in this season. It's okay because we're in physics. I follow the order when we're in physics. If I'm in math, I'll go out of arm's way because I'm a physicist and I'm savant with math. Because physicists are naturally savant mathematicians. So other than that, what I was just trying to explain, so if you ever take a course called differential equations, and usually it's ordinary differential equations, there are partial differential equations. The internet will tell you that they're harder, but they're actually the same level. It's just a notation is all it really is. When we get into sound, and I think I showed you partial integrals already, you just don't even realize you learned them on these videos. That's the cool thing with physics, is you don't realize that you're learning the higher level stuff but you're learning it. You just don't realize it. Other than that, like differential equations. So there are two ways to solve differential equations. Now, if you're a physicist, which I am, I'm a physics student, a physicist would guess a differential equation. I don't like guesswork because it's too, it can be tedious and time-taking. The second alternative is using a system of linear equations. So a system of linear equations is like taking a matrix and you're reducing it. I will try to show you what a systems of linear equations are. If I can find them. We've actually done them without even realizing it. Okay, so a system of linear equations is when you have two linear lines. So in a graph, right? And since we're doing linear momentum, we're going to cover linear equations. So let's say if I have a graph. Now we don't care about curves. In linear momentum, we do not care about curves. But let's say if I have a graph, right? And then I have 1, 2, 3. These lines are a little off. I just gotta find points. Hold on. Points of intersection. 1, 2, 3. Okay. This is good because we've only covered parallel when we got into energy. All right. Now, there really are supposed to be two lines. Well, I guess we could do both. It doesn't really matter. I mean, the second graph is just one line. Let's say if we have two lines, right? This is an elementary way of explaining this because systems of linear equations is elementary, and you'll know in a second. Let's say we have two lines here, right? And I trace this out to one line. I want to come up with two equations for that line. So something like this would have no solution. Right now, I'm just showing you the math before we get into the physics. No solution. Now, if I have one line, I have infinite. So you can think of infinity, infinite solutions. So now we talk about the infinity. Okay. And what's interesting is you don't really talk about infinity in General Physics 1, in Newtonian mechanics. We talk about it when we get into electricity and magnetism. Now let me show you this other graph. So if I have something like this, just bear with me on this video. I know I'm being a little slow, but I'm a little rusty. Do that one. And then this one. So imagine these two lines come into a collision. One way to think about it is that there's two particle paths, right? And they're going into what we call a collision. Right? This is the collision. Two lines hitting a collision. And this has exactly one solution. So exactly one solution, no solution, infinite solutions. Okay. Now I'm going to show you some equations. So for this one, you could have two equations, right? You can have x1 minus 2x2 is equal to -1. negative x1 plus 3x2 is equal to 3. So there's exactly one solution. Now, why don't we try to set this up in an augmented matrix? So if you wanted to put this in a matrix, right? This whole thing in a matrix, I would do 1, negative 1. Or you know, we're going to do it on a separate page. So the second one, you're going to have x1 minus 2x2 is equal to negative 1. Negative x1 plus 2x2 is equal to 3. And then the infinite solutions is going to have x1 minus 2. Let me rewrite this for you. x1 minus 2x2 is equal to 1. Or x1 minus 2x2 is equal to negative 1. Negative x1 plus 2x2 is equal to 1. Okay. I think now what we're going to do is we're going to take these numbers and we're going to put them in a matrix. Making sure that you could see both pages here because it's going to be really hard to teach this. Okay, or explain it. All right. So the one that has exactly one solutions, let's put it in a matrix, right? 1, negative 1, negative 2, 3, negative 1, 3. 1, negative 1, negative 2, 2, negative 1, 3. And these ones are pretty easy because you just have to add the numbers to get this reduced. Like I could probably reduce these because these are elementary matrices. Not only they're elementary, whoops, we got to be a numerical. 1, negative 1, negative 2, 2, negative 1, 1. Okay. Now we're going to do some linear algebra. All right. Now, linear algebra is a really fascinating course. You actually don't even need a calculator to do linear algebra. It's really fun. Oops. I hate when that keeps falling over. I have like a $10 tripod. It's not a very good one. One thing I gotta do is get a better tripod for the next season. All right. So the idea is we want to get this number 0 below. So what we're going to simply do is add the two rows. So if I add these two, I'm going to basically get 1, 0, negative 2, 1, negative 1, negative 1 plus 3 is 2. And we have to get this 0 as well. So I just made the bottom this 0. We got to get this top 0. So how would I make this 0 is I'd have to multiply by 2 and add it. Okay. Basically, I got to multiply this by 2 and then add it. So 2 times 0 is 0 plus 1 is 1. 2 times 2 is 1. Or 2 times 1 minus 2 is 0. And then 2 times 2 is 4. Right? And 4 minus 1 is 3. All right, we could check it. We could check it on the calculator. Whew. Long day. I hope this video doesn't get too long. Stupid stuff like that, like a tripod falling over and a calculator that has to load to turn on, is going to do crazy things like that. Slow down this video. Probably not much. Alright. Sorry I'm a little negative, Nelly. I'm just trying to get... I would like to get these things working, you know? Menu 7, 1, 1. So this is going to be a 3 by 2. Alright, it's a 2 by 3. Hold on. I haven't done linear algebra in a while. This calculator trick, it works a lot better when you 1, -1, -2, 3, -1, 3. And do menu 7, 5. Yeah, I reduced it. See, if I reduce it, I get 1, 0, 0, 1, 3, 2. This was an elementary matrix. And because it's an elementary, because it's just simply system of linear equations, this is the most elementary form there is. Alright, so that's if you reduce this one. This is just telling you that x1 is equal to 3, x2 is equal to 2, and then we say x3 is free. And then I guess if you want to put it in parametric form, you'd have to do this. So you'd have to do x1, x2, x3 is equal to 3, 2. We said x3 is free, which means it has to be equal to itself. I think if it's free, it's 1. I can't possibly remember. I just remember when we have it, we don't include it. So the vector x should be equal to, or we do a. We do the vector a is equal to x1 times 3 to 0 plus x2 I did this wrong. Hold on, just bear with me. Vector A is equal to x1, and we did x1, right? So this should be 3, 0, 0 plus x2 times 0 to 0. I think it's something like this, but you don't have to even worry about parametrics. It's just the fact that you get x1 is equal to 3, x2 is equal to 2, x3 is free. What this is saying is if you run these numbers into these equations, you'll get the same value. So whatever number that I put in equation 2 will give me the same value when I use 3 for equation 1. That's what that means. So what they are saying with this is, I think we can go back and check it. So you're going to have x1. There's a way to do this and I can't remember, but you have to basically use these numbers and you put them in your equations. And I can't remember off the top of my head how this is done, but you can check them. Let me see if I can find one. Might be the next section I'm talking about here. Yeah, so all this means is that if I take this equation, I ran 2 for x2, and I run, you'll get the same value. So we say, and what this means is that 3 is equal to 3 and 2. And what they mean by these values is that 3 is equal to 3 and 2 is equal to 2. They call this an identity, right? This is an identity. So I guess you would... So I guess you could do 3 times 1 plus negative 2 times 2 is equal to negative 1, right? 3 times 1 is 3, minus 4 is equal to negative 1. See how magical this is? Look. When you set the numbers, you work with these numbers here. 3 times 1 plus negative 2 times 2 is equal to negative 1. 3 minus 4 is equal to negative 1. Negative 1 is equal to negative 1. This checks out. And then you do the same thing with the second equation. So you could say negative 1 times 3, right? Plus 3 times 2 is equal to 3. Negative 3 plus 6 is equal to 3. 3 is equal to 3. Okay. Now, what I just showed you past the reducing part is what they call a system of simultaneous linear equations. So, basically, this is a very easy approach. This is not a guesswork way, as you can see. What you're doing is you're reducing the matrix and you're plugging values in after you reduce it to see if the equations check valid. There's an identity, so negative 1 and 3 are the same. That's what gives us what we want. See, we took these two and ran them. This is the method of simultaneous linear equations. And they've done these in Japan, in Japanese mathematics. Okay, let's do 2 more. Well, I guess if it's no solution, we'll find out what happens when we reduce this one. So let's do the one that has no solution. Now, obviously, all I'd have to do is add, right? I get 1, 0. Ah, that's why it has no solution. Negative 1. Negative 1. 2. Now, I wonder if that can get reduced any further. We got 1, negative 1, negative 2, 2, negative 1, 3. All right, we can still reduce this a little bit more. They want this 0, it looks like. How you would make that top 0 is you would have to multiply downward by, you have to multiply by, I think you have to multiply by a fraction. We want to get this top number 0, 2 times 1/2. Right? Would give us 1. So I guess you would multiply by 1/2 because 2 times 1/2, right? 2 times 1/2 is 1. 1 plus 1 is 0. So then this would then give you 1, 0, negative 2, 0, and then 0, 2. Or 0, 1? Oh, I see what they did. I see what they did. So you'd have to divide by 2. You simplify this. You divide this bottom row by 2, which is the same thing as multiplying it by 1/2. And then you're going to get 1, 0, negative 2, 0, negative 1, 1. And then you would just simply add this row to this row. And then you would end up getting 1, 0, negative 2, 0, 0, 1. Okay. That's if you reduce it. And then you could say that x1 minus 2x2 is equal to 0. And then x3 is free. So this one has no solution because there's an equation that has 2 unknowns and 1 known. So unless we knew what one of these is equal to, we wouldn't be able to solve it. So there's not much else we can do with this equation, because we don't know what one of those values are, because there's no constants. Let's look at the one that has infinite solutions. So exactly one solution was good. So infinite solutions is you're going to have 1, -1, -2, 2, -1, 1. And I guess if we add it, we'll get 0. So you get 1, 0, 2, 0, -1, 0. And you want to make that top 0, it looks like. Let me see what happens when I reduce it. You can see why there's infinite amount of solutions, because it's all zeros. So we got 1, -1, -2, 2, -1, 1. Yeah, you can't simplify this any further. This is your answer. So basically what this is saying is that in equation terms, this is x1 minus 2x2 is equal to -1. There is no free variable because it has infinite amount of solutions. So we can't say that neither of these x's are free. But it is possible we could say that x3 is free, but there's an infinite amount of solutions, so I don't think there would be a free variable here. But as you can see, first case where we had a collision, we were able to figure out the systems of linear equations. And this is how linear momentum works. With energy, is very difficult. When we do linear momentum problems, you're not really going to be dealing with these kind of graphs where you have a parallel going on or just one line itself. We only worried about the parallelness when we did energy. See, energy is difficult. Energy acts more like no solution or infinite amount of solutions. Linear momentum is different. It acts more like the collision perspective, so it acts like exactly one solution. So in physics words, and in a physics viewpoint, it's that energy is a hard topic, but once we get to linear momentum, it saves the day. So a lot of times when you take, like, when you learn energy, you'll get linear momentum with it to breeze down your backs a little bit. Now, you do have to use vectors, though. They don't cancel. Remember I just said momentum is a vector. It's a position. That's what it really is. Other than that, what I was all talking about, you're probably like wondering, what book is he talking about, or what Japanese mathematics? Okay, there's this really good book that was written in 1912. And it was written by a mathematician. It's called A History of Japanese Mathematics. It's a very good book. You should check it out. You don't have to buy this one. Other than that, this is the crude way of understanding the area of a circle. And then you would have like something like matrices and magic squares, magic circles. I'm trying to show you this little illustration of these people standing in a circle. Here we go. This is one of their puzzles. It talks about all these people. This book was actually written in 1912. It's a very old book. And it's actually not the latest book. He wrote a history of mathematics, but this was written by David Eugene Smith and Yoshio Mikami. You can get this book online as a PDF, and it's free to use. It's an archive book. It is a history book, but it's the history of math. So it's not really historical at all. When you have like a history of any science subject, it's more of a science book than a history book. A historian would not understand this book because it has equations in here. I mean, it's got all these crazy gobbledygook equations. I mean, this book is so old that they even have like a free PDF of it, but it has all these, I'm just going to skim through the book, but it has all of these, this is like an area of an ellipse. It's got all these crazy math in here that I don't even think a historian would be able to understand this. I mean, they would understand like the person that wrote the stuff, but they wouldn't really understand what he was trying to explain. And that's my job. My job is there to understand the work. But I also am interested in who came up with the work. But like I said, my job goes further than a historian. I want to know what the work means. All right, enough of that. Let's get into physics. I think I kind of covered everything. There is going to be center of mass in here. If we do need to cover orthogonality, I will squeeze it in. It might make this video really long, like energy. It might make it like energy, so I don't know if we're going to use that, but we'll see. We'll see. I haven't covered it in the last episode, and I said I would, and the thing is, I'm afraid to touch it because it covers in rotation. Doesn't really apply much with linearity, but the center of mass is important because it's like our bridge between the linear and the rotational world. And you're going to find out that the rotational world is actually wants to be in like the linear world. It acts like it's in the linear. It's very like narcissistic in a way. It's like, I'm not in a rotational world, I'm in a linear world. What's so rotational about it? I don't see rotation. It's very in denial. It's really in denial. Like, it's funny. They use the J vector for momentum, which we are going to explain. We're not using, well, I think they use J for impulse, but we are not using I. I'm not using I. I'm not using a capital I. I'm using J. We're really just going to cover particles. That's really what I want to do in this. So we'll skip anything of a right, like anything of you know, like if you're like a bullet comes out of a rifle, ball hitting a wall, we're going to skip any of that. What I care about is we deal with particles. So we're going to do collisions. We're actually going to just do collisions because momentum is a very difficult concept. That matrix stuff I showed you is the mathematical foundation that goes into collisions. Because remember that one graph I showed you, the lines intersect. Very important to understand. Okay, this is a really fun problem. So we're going to do moderating fission neutrons in a nuclear reactor. We're going to use fresh paper. That's just pure math. We're going to use applied math, which is physics. Okay. Moderating fission neutrons in a nuclear reactor. The fission of uranium nuclei in a nuclear reactor produces high-speed neutrons. Before such neutrons can efficiently cause additional fissions, they must be slowed down by collisions with nuclei in the moderator of the reactor. So what a moderator is it's a device that slows down the nuclear process. There is another book that you should check out. It's called Driving a PWR. The words PWR stand for pressure water reactor. If you're into nuclear engineering or understand how power plants work, or even want to be involved with the safety of keeping them safe for the future, which I hope to do is my job goals. I want to design safety measures for nuclear power plants, but I want to do it theoretically. So I want to do it through computers and not actually be on the site. But other than that, that's what a moderator is. It's kind of like your gas tank. A moderator is like your gas tank to your car. So it's like it's something that holds fuel. It's sort of like a propane tank that holds propane, or a gasoline tank that can hold gasoline. It's something that can store fission, but they put the fission, it doesn't really store it. They kind of like, it really kind of channels through the device. It's just like when you put food in your stomach and then it comes out of your digestive tract. It's the same idea when you pour gas in your car and it comes out in your exhaust, your tailpipe, and it goes all over the engine and everywhere. A nuclear power plant is not much different than a car. Other than that, I explain what a moderator is, and I'm telling you, what the problem I'm going to explain is not even going to do that. That's a moderator. The first nuclear reactor built in 1942 at the University of Chicago. Now, it's funny how they don't even tell you the name of this, and I will tell you the name. It's called the Fermi Lab. Used carbon graphite as the moderator. Interesting. And you know why? Because that's where they started with their fuel rods. Now, there's only one country that uses graphite. There's only one country left in the entire world. And it's in this book. If you ever check out how to drive a pressure water reactor, it'll tell you. The only country in this world that still uses a graphite is North Korea, believe it or not. They're the only country that uses a Magnox reactor, which is basically the same thing as Chernobyl. An RBMK is a hybrid of a Magnox reactor. So, yeah, I mean, that's unsafe, because graphite is very cheap to buy, quick to manufacture, but it's delicate because it's solid. It's like a rock or a crystal. It's going to break. So a lot of times they like to use uranium instead of, or plutonium or neptunium, depending on what is better. But they'll use the other ones because they're more safer. Other than that, you're learning some nuclear physics. At least from the, not from the atomic perspective, but you're learning it in the work field. Now, I don't work in any kind of nuclear power job. I just read a lot of I read books about it. And I'm not, you know what, it's not like, you know, it's not like overseas just told me this stuff. I just, like I told you, there's this book you gotta check out. It's written by Colin Tucker. I wrote a book report about it, by the way, of why we need nuclear power plants. I mean, Cape May is like completely dead with no power. We got all these brownouts all the time, and like I said, all our power outages could be solved if we would have one down here. It would provide jobs and everything. And I don't know, the county just doesn't want them for some reason. But it's silly not to have one. I think it's silly not to have one. I'm just going to leave it at that. All right. The first nuclear reactor built in 1942 at the University of Chicago. By the way, it was a football field. This thing was underneath a football stadium. Used carbon graphite as the moderator. Suppose a neutron mass 1 mu. Mu is an AMU, which is an atomic mass unit. That's what U means. That's a 1 atomic mass unit. Which you'll learn about in, I think you'll learn about that in general physics too, when you cover electricity and magnetism with electrons. All right. Mass is 1 U traveling at 2.6 times 10 to the 7th meters per second. Undergoes a head-on elastic collision with a carbon nucleus mass of 12 AMU. Atomic mass unit. Initially at rest. Neglecting external forces during the collision, find the velocities after the collision. 1 AMU is the atomic mass unit, equal to 1.66 times 10 to the negative 27th kilograms. Now this section is very interesting. This chapter we're going to be touching, we're pretty much going to be tapping into chemistry when we get into linear momentum and center of mass. And that's why I like these problems here. Okay. This is an easy problem. Other than that, this is the weak nuclear force that we were dealing with. That's why I like this problem. Most Newtonian mechanics, they don't really like to go into this stuff. They only like to stay at gravity. Gravity, and like, they only want to stop at gravity and not get past that. Alright. I like to go to the high level stuff. I like to show you the new stuff. I like to show you like the most like modern stuff. That's why I kind of leaked modern physics in this season, even though it's a weird thing to do. I kind of smeared it in here. All right, it's good to know. All right, so if I wrote this out, and I'm trying to get a better view of it, so I'm going to have V. So we're not going to say before and after. We're going to say initial and final. All right, so initial, you're going to have V. This is velocity, by the way. V sub n 1x is equal to 2.6 times 10 to the 7th meters per second. Which is a fast speed. I mean, light is 3.0 times 10 to the 8th. This This thing's flying. I mean, this thing's going faster than an electron. All right, and then, so initial, you're going to have this, and then you're going to have this neutron, we said it was? Yeah, a neutron. Which a neutron, believe it or not, has a neutral charge. You're not even going to worry about charges in Newtonian mechanics, but neutron has a neutral charge. So m sub n is equal to 1. I'm going to say AMU. I'm not even going to write U. U could be anything. U could be a constant, but it's an AMU, which is an atomic mass unit. And then this is a carbon particle. It's really a particle. This is a carbon particle, which is much bigger. And then it's going in the x direction is all they're showing you. It's just traveling in the x direction. And then the mass of a carbon is equal to 12 atomic mass unit, 12 AMU. AMU is a constant of 1.66 times 10 to the negative 27th. So that's what 1 is. If you have 12, you just multiply that by 12. Okay. Now, I haven't had chemistry yet, even though it sounds like I know chemistry. It's just, I've had physics twice. I had college physics 1 and 2. And then I had calculus. I took all the way up to Calc 3. And then I took general physics 1 and 2. And I'll be taking general physics 3 in the fall. So, yeah, I mean, get a physics degree. They're very important. They're very good. All right. Other than that, you got the after. Oh, we don't want to say, we're not going to say before, after. We're going to say initial and final. I don't want to say before, after. All right, so this is like right before the collision takes place. And then this is like right after the collision. So by the way, this is the neutron. This does not mean on. This is the neutron. This little circle. This thing's a neutron. And then it's going this direction. V sub nx is equal to what? And then the carbon is going this way. I'll just make the arrow big. It's okay. And then you say V sub c 2x is equal to what? Okay. So the idea with this problem is, in a nutshell, you treat this one as one equation, and then you treat this one as a second equation, and you have to do what's called a method of simultaneous systems of linear equations, but you're not going to use the matrix method. You're going to use it using algebra. So that method is nice because it shows you an alternative. I guess you could use either one. So, other than that, they're just saying we neglect external forces, so momentum is conserved in the collision. The collision is elastic, so kinetic energy is also conserved. So the reason why they're saying conserved is because external forces are non-conservative. Internal ones are conservative. So there's nothing that's non-conservative because it's being ignored. Now, what's interesting, if you're in General Physics 3, you're going to actually consider fluids. Fluidity as a part, but not in here. We take the x-axis to be in the direction in which the neutron is moving initially. The collision is head-on, so both particles move along the same axis after the collision. The carbon nucleus is initially at rest. We replace A by N for the neutron and B by C for the carbon nucleus. We have M sub N is equal to 1. We've got all that. The target variables are the final velocities, V sub N 2x and V sub C 2x. Execute, you can do the arithmetic. Hence, there is no reason to convert atomic mass units to kilograms. The results are, so V sub N, oops, let me write that right. V sub N 2x is equal to let me clean this up a little bit. So V sub n 2x is equal to negative 2.2 times 10 to the 7th meters per second. And because it's negative, it means it's traveling in this direction at 2.2 times 10 to the 7th meters per second. And that's just the neutron. And then the carbon is traveling, it doesn't even look like a carbon. Is 0.4 times 10 to the 7th meters per second. So you could see it's traveling at the same amount, but it's close. This one, the carbon's going slower, but the neutron is going slightly faster in the negative direction, and the carbon is going slightly slower in the positive direction. The neutron ends up with m sub n minus m sub c divided by m sub n plus m sub c. Oh, that's interesting. Okay. And they took the absolute value. So what they did in the math was they used m sub n minus m sub c divided by m sub n plus m sub c, and that got equal to 11 over 13 of its initial speed, and the speed of the recoiling carbon nucleus is 2m. Interesting. So you got 2 m sub n divided by m sub n plus m sub c is equal to 2 over 13. Because the denominator is the same. It's m sub n plus m sub c. Of the neutron's initial speed, kinetic energy is proportional to speed squared, so the neutron's final kinetic energy is 11 over 13 squared, which is, so if you took this 11 over 13 squared, it's approximately 0.72, and that's 72%. This is equal to 72% of its original value. After a head-on collision, its kinetic energy is 0.72 squared, or about half its original value, and so on. After a few dozen collisions, few of which are head-on, the neutron speed will be low enough that it can efficiently cause a fission reaction in a uranium nucleus. So it has to have several collisions to do that. Okay, now the next thing we're going to cover is we're going to do center of mass. We're going to do it of a water molecule. I think that's the next example. And then we got some rocket propulsion we can do if you want. Acceleration of a rocket, I guess we could do. And I'm not going to do a rocket propulsion. You know what? Just skip that. If we have time, we'll do it. Center of mass of a water molecule. This is an equilibrium problem, by the way. Center of mass is the same thing as equilibrium. Think of the center of mass as the sum of the forces equal to 0. Momentum is more like every force is equal to a negative and opposite reaction. You can think of a collision like that. And then the momentum is the force is equal to mass times acceleration. And then that's when we think about momentum. It's the force is equal to mass times acceleration. A collision is the equal and opposite force. When we think about center of mass, it's this force is equal to 0. Okay, center of mass of a water molecule. So we have a simple model of a water molecule. The oxygen-hydrogen separation is equal to 9.57 times 10 to the negative 11th meters. Each hydrogen atom has a mass 1 AMU, and the oxygen atom has mass 16 AMU. Find Find the position of the center of mass. I said portion instead of position, but it's kind of the same thing. It's funny. Solution: identify and set up nearly all the mass of each atom is centrated in its nucleus, whose radius is only about 10 to the -5 times the overall radius of the atom. Hence, we can safely represent each atom as a point particle. All right, let's get started with this. So, this, like I said, this video is a lot like chemistry. It's a lot like General Chemistry 1, actually. So, what's happening here is that we're going to have a water molecule. Now, these aren't very good drawings because you're not supposed to have spheres over spheres. Let me fix this. So, you got a water molecule. It's got like these little things around. You know what? I like this picture better because it's symmetric. We got symmetry here. All right. And then I take like a Cartesian plane inside, and then I notice that the center here is going to be equal to the center there. And then we got little dots here coming out. And then we use some geometry to figure out the center of mass. Alright, this is how physics, it trumps every other science. 105 degrees, X, and this is a hydrogen. What is hydrogen? Is it O2? It's H, right? We'll call this H. H means hydrogen, right? And then oxygen is just O2. Or oxygen is O. We don't need bases. Let's do O for oxygen, H to hydrogen. So when you have two hydrogen and one oxygen, got 1, 1, and 1, this gives you H2O, 1, which is basically H2O. Okay, there's a little chemistry. There's some chemistry there. All right. So the oxygen atom is at X is equal to 0. So you're going to have X is equal to 0. Y is equal to 0. Or you could say that XY is equal to 0, 0. Which is, we're saying that XY is equal to the origin. Which is this piece right here. This is the origin. That's, you can think of this as the origin. That center right there. All right, now we're going to do center of mass. So when you write center of mass, you're going to write com, which just means, well, I can spell it out. So center of mass in the x direction is equal to 1 AMU times D cos. And we know D. We do know the value of D. D was given to us. I'm trying to see where I can find the value. D is equal to 9.57 times 10 to the negative 11th meters. So we know D. We know D in this. We know D. D's given to us. So X center of mass is equal to 1 AMU times D cos. I'm going to write... We're going to say D cos theta. And theta, we also know theta is equal to 52.5 degrees. In case you can't really see that, theta is equal to 52.5 degrees. So we know theta and we know D. D is equal to 1 AMU. You know what? I'm not even going to put that as theta. I'll just give you the degree. So X center of mass is equal to 1 AMU times D cos of 57.5 degrees, right? Plus 1 AMU times d cos of 57.5 degrees plus 1 AMU times 0. All right, so this turns to 0 when you multiply it by 0. All you're left with is this and that. And then this gets equal to 0.068D, which we know D, by the way. And that's just in the X center of mass. The Y center of mass, I don't know if I could fit it. Made so much of a mess. I guess I could squeeze it down here. So Y center of mass is equal to one AMU times D sine 57.5 degrees plus 1 AMU times negative D sine of 57.5 degrees and then plus 16 AMU times 0. Okay. And then this is 0. This cancels out, so this is a negative, this is a positive. So this whole thing just goes to 0. 0. This together is 0, so it's 0 plus 0, which is just 0. Okay. The center of mass is much closer to the oxygen atom located at the origin than to either hydrogen atom because the oxygen atom is much more massive. The center of mass lies along the molecule's axis of symmetry. The center, if the molecule is rotated 180 degrees around this axis, it looks exactly the same as before. The position of the center of mass can't be affected by this rotation, so it must lie on the axis of symmetry. Now, what's interesting is symmetry is more important in when we get into electricity and magnetism than it is to Newtonian mechanics. It's more important in general physics too. Other than that, that is a center of mass problem. Don't want to do rocket propulsion. We're going to skip it. And the reason why is it's a lot like a kinematic equation. It's basically the same thing as the kinematic equation. So you're going to have a differential of mass over a differential of time is equal to some, that's what you have. I'll put it in the summary. Yeah, I'm not going to do rocket propulsion because we've covered stuff like this in kinematic equations. Don't know if there's any more problems in the next section. Those were the two I wanted to show you. They were very important. I think it's just one chapter. I think that's it. I thought there would be 2 chapters to cover. Huh. You know what? I'm gonna skip rocket propulsion because it's not really ideals for black holes. I will get to the summary now. I didn't realize that this was on one chapter. Okay, so the stuff about rotation, we're gonna cover that next week. So if I haven't showed you anything on rotation yet, the only part that I showed you about rotation is where I explained about the angle between 2 vectors. And then before then, I even talked about how we have projectile motion. It's something else. That's kind of it, but that's not really what it is. we'll cover rotation. I'm going to do orthogonality. I didn't realize that this is like in one summary. I thought there'd be two on momentum. See, like I said, usually when momentum is brought up, they combine it with energy, and I broke the rules a little bit because I'm like, yeah, it's too much. Because energy like deserves a story. Like that deserves 2 hours of explaining. So back when we did energy, I showed you the dot product, and I showed you how to do what's called the Gram-Schmidt process. I didn't show you orthogonality, and the reason why we're going to do that is because we're going to touch into comets and stuff like that. It's really something from straight up from linear algebra. Trying to find the one with the comet. We're gonna be doing a lot of. I'm gonna do every comet problem we can find, basically. Trying to find the page. No, it's not a projection. We're not gonna do any projections. That's not really the thing of this course. Linear transformations I will get into when we get into rotation. It's going to get interesting. When I do rotational momentum, not rotational kinematics, but when I show you rotational momentum, there's going to be some linear we're going to learn some linear transformations, which actually play a lot with differential equations. They help a lot. So you'll learn even like if you're not a physics person and you wanted to have to take differential equations, I mean these videos, the way I'm presenting them is perfect for that. I just haven't taken the course to explain it. I know there's these examples in the back. There's a picture of them too. I think I went a little. You know what? That's another, we're going to do least squares. We covered orthogonality when we did the Gram-Schmidt process. We're going to do least squares. I said the wrong thing. I just want to see how least squares is done. Oh, I know what we'll do. Even better than doing a Halley's Comet problem, I'll show you at least squares. So this is where we get into matrix multiplication. Now, it's not the multiplication that I showed you, it's a different form. So when you do a method of least squares, which is really an application in statistics, but it's in linear algebra. So if I take the A and I raise it to a period times A, or I don't even know what T stands for in linear algebra, but it's A raised to T times A. So this is an invertible matrix, is what they're saying. This matrix is invertible. I think T stands for transform. So it's a good thing I'm showing you this because we're going to be doing linear transformations when we get into the next couple of episodes, and I'll show you which, and I'll let you know which one it is when we're done with this. So you're going to have 1, 1, 0, 0, 1, 1, 0, 0. This is an easy one because there's just zeros in here. 1, 0, 1, 0. See, when you take matrices, zeros are like the nicest thing to work with. 1, 0, 1, 0. You can't really see that. This is 1, 0, 1, 0. I'm going to redo this. All right. Got 1, 1. How many are there? 1. Okay, there's 6. 1, 2, 3, 4, 5, 6. That's a 0, by the way. I just screwed it up. All right, this is what we call matrix multiplication. And one way to think about it is it's a scaling multiplication, so there would be like a dot product in the middle of this whole operation here. That's another way you can think about it, because this acts as a scaling multiplication. I didn't cover this in energy, so I just thought I'd quickly cover this. You're going to get a matrix that looks more like the first one than the second one. So you're going to have 6. All right. And that's if you do the AT of A, and then if you want to do the AT of B, by the way, B is a vector, you're going to get this thing. By the way, this matrix is the A of T, this is A. So the first part's the same. Running out of room, but you still have the scalar in there. -3, -1, 0, 2, 5, 1. So these are separate. This is what a vector matrix would look like. It's just that. It's just that. And then this gives you 4, -4, 2, 6. Gives you another vector. So this is more like the cross product, which I haven't really showed you, but it's really a scaling. It's just, it gives us another, it acts more like the cross product. I haven't showed you that. When we get into linear momentum, you'll learn all about that. And then you have to take the augmented matrix. Oh, I see what they did. So you're going to add this to this column. If you want to take an augmented matrix, you would just add this over to here. You have 6, 2, 2, 2, 2, 2, 0, 0, 2, 0, 2, 0, 2, 0, 0, 2, 4, -4, 2, 6. And then I want to reduce that. I'm going to end up getting 1, 0. 1, 0, 0, 0, 0, 1, 0, 0, and then 0, 0, 1, 0, 1, -1, -1, 0, 3, -5, -2, 0. If I reduce it. Okay. And then you have a general solution. If I take the general solution, which is just the systems of equations, you're going to get x1 is equal to 3 minus x4 x2 is equal to -5 plus x4. And then x3 is equal to -2 plus x4. And then we say that x4 is free. Okay. And now we want to run the vectors. If we want to put it in a vector form, we just say for x, and want to put it in what they call a parametric form, you're going to get 3, -5, -2, 0, plus x to the 4th times -1, 1, 1, 1. Okay. That is how you do least squares. Not something you really need to, I actually don't need to worry about linear algebra, but that is the math for what you're doing. So, let me show you the summary, and then we'll talk about the next, we'll discuss the next episodes before. Let me jump to the summary first. All right. I guess we could use this sheet. I'll just use another sheet because that was just math. Let's go back to physics. All right, so if you want to talk about momentum of a particle. Now, like I said, remember that force is equal to mass times acceleration? Well, instead, we're going to now say that the momentum is equal to mass times velocity. Isn't that interesting? We turn acceleration into velocity, force into momentum. So there's a little similarity. So then we say that momentum, so just ignore all that, but now we say that momentum is equal to mass times velocity. And then the sum of the force is equal to d momentum dt. And then if you want to know impulse, impulse is the action being made to do, to act. It's like something you do with momentum. Impulse is like something you work on. So if we want to know impulse, which we call it the J vector, and J vector also means Jacobian if you're in Calc 3, by the way. But we say that impulse is equal to the sum of the force times time final minus the initial time, right? The final minus the initial, which is equal to the sum of the force times the change of time. See, when you have time, you have impulse. When you don't have time, you have momentum. When we put time into account with momentum, it gives us impulse. And then you could say that impulse, and this is pretty much how the rocket problem was looking like. It was this form of math. Impulse is equal to the integral of t from t initial to t final of the sum of the force dt. It's a line integral. Impulse is equal to the line integral from the initial to the final, which is the sum of the force dt. This is a FTC integral. And then after this cancels out, you then say that this is equal to, actually that's not correct, but if you integrate this entire thing, you're going to then get impulse is equal to final momentum minus initial momentum. All right, and then conservation of momentum, it follows conservation of energy. So if you want to know conservation of momentum, this, and by the way, this is all impulse. This is momentum. Yeah, I know we didn't do an impulse example, but we did momentum. And then momentum is equal to momentum A. This acts like a lot like relative velocity, by the way. Momentum A plus momentum B. It acts sort of like relative velocity and center of mass almost. And then this series, so momentum is equal to momentum A plus momentum B plus the series, which is then equal to m sub A. Momentum, oops, I didn't write that correctly. M sub A times V sub A plus M sub B times V sub B, plus so forth. And then you say if the sum of the force...
Yes.
What?
You moved my thing.
Doing a video.
You moved my container. Can I have it?
Sum of the force is equal to 0. We then say that momentum is constant. Alright, so say the sum of the force is equal to 0, momentum is constant. And this is conservation of momentum, which follows conservation of energy. Alright, that is pretty much it. Other than that, there is one more part. I have to show you center of mass. I gotta put it on a separate sheet. So for center of mass, which is very important for the next episode. So center of mass center of mass from position is equal to m1 position 1 plus m2 position 2 plus m3 position 3. It's a series is what this is, plus so forth, divided by m1 plus m2 plus m3 plus so forth. And that's mass. M is mass, R is position, which is the radius. And then we say that this is equal to the sum of the force. Well, that's not correct. It's not the sum of the force. This is equal to the sum ith. The ith sum of mass of the ith sum of the position, ith position. And when you think of ith, you can think of it as an infinitesimal or differential. A differential element divided by the sum, the ith sum of the ith mass. Now another better way to interpret it is you would say the sum of I to n, and then you would have mi ri over the sum of I to n, and you usually get a value for I of mi. That's what this I thing means on the side. It's the sum from I to m. All right, and then momentum is equal to momentum is equal to m1, velocity 1, plus m2, velocity 2, plus m3, velocity 3, plus so on. That's what they're showing you there. And then this equals to m center of mass. Alright, and then this is where we go back to the Newton's law, third law. So we say the sum of the force, sum of the external force is equal to mass times the center of mass acceleration. Okay, now that is momentum. See, in energy, when we did energy, we cared about the external forces, and we still do when we get into linear momentum. So this is everything you need to know about linear momentum. Now, the next two episodes are supposed to be called angular kinematics. I'm not going to call them that. You won't even hear the word angular other than the comparison. It's going to be called rotational kinematics. And instead of doing angular momentum, we're going to call it rotational momentum. But it will be 2 episodes, 2 videos, because it's a very, it's like this chapter, but it's like, there's like 2 of them. But I don't think it's going to be as bad as this one. But there's a lot of good examples in angular kinematics and angular momentum. So we probably will be doing some, we won't have to do any linear algebra until we get to angular momentum. Angular kinematics, it's just like kinematic equations. We can get started with the equations and go for them. I like to explain a video on them because a lot of times they don't really get to be like for anyone's knowledge, but they're really good to know as angular kinematics. So stay tuned on those 2 episodes. We're going to be doing rotation. We're going to be in the rotation world by next week. So that is the next 2 videos. Other than that, we'll be doing gravitation after that and black holes. So we've covered pretty much everything we need to know about gravitation. I mean, we just did center of mass, and we did momentum. Momentum wasn't really the important part. Center of mass was. It's just a really cool application. I just thought I would show you. Other than that, wow, this video is 1 hour and 28 minutes. Huh. Okay, well, it's not as bad. I thought it would be 1 hour, but 1 hour and 20, but I guess it was close. All right, well, stay tuned. Next week will be rotation. Thanks.